Going to record a little video of the lab exercise 4, RLC frequency response. Welcome to lab 4. So in this exercise, we'll be measuring the steady state response of a capacitor voltage in the RLC circuit shown in figure 1.4 with an AC input. So we have an RLC circuit, and in your homework, you've actually analyzed some pretty similar RLC circuits. So it should be pretty familiar to you. One difference is that we have a source resistance or a source impedance that we need to take into account. And that comes from the fact that we're going to use a function generator for the source instead of a controlled or a regulated source. So since we don't have a regulated source this week, we have to model our source as having an output impedance. As is standard for many function generators, the output impedance that we're going to work with is 50 ohms. So it says it right on the front panel of our function generators, so no mystery there. We could measure it, but it's probably a pretty good value. Okay, great. We'll record the data by hand, so no lab view this week. We'll get back to it though very soon. Enter it into a data file in MATLAB, plot the data, derive an analytic model, and compare the analytic model to the data. So a lot of familiar steps, but we're not using LabVIEW this week to gather the data and record the data. The objectives of this lab exercise are for students to explore steady-state circuit frequency response, to deepen their understanding of RLC circuits, to learn to better measure AC voltage with an oscilloscope, to model real circuits and compare the theory and experiment, and to get a sense of resonance in a circuit. So, resonance is a concept that we're only going to really be able to scratch the surface of right now, but the idea is that at certain frequencies, if you put an input into a circuit for certain types of circuits, you can get an output that's larger than the input. So conservation laws do still apply, so don't worry. Energy is conserved. We haven't found free energy. But the resonance phenomenon is something that's really cool. You're going to explore in more depth in system dynamics next semester, and in vibrations in your senior years. So yeah, there's a lot of cool stuff in the idea of resonance, and we're already able to analyze resonance in this class, but we're just really getting a feel for it right now. The idea is that we're going to be able to put a voltage in at a certain frequency that resonates the circuit. It's like if you think of a swing, and if you let a swing just swing back and forth, if you maybe are on a swing and you're kicking and you're getting yourself up to a certain amplitude of oscillation, and you just let yourself oscillate, that's the sort of natural frequency of the swing. And if somebody pushes you at that frequency, your amplitude increases. Whereas if you're at a different frequency, it does not. So resonance has all kinds of really cool applications, and it's something that we're going to see happen in this lab. We may not completely understand it yet, but at least we're going to get to measure it and analyze it. So yeah, great. Materials. So the following materials are required. So a function generator, that's going to be our source. An oscilloscope, that's how we're going to measure the output and the input to the circuit. A multimeter, a breadboard, 4 male-to-male jumper wires to make it easier to probe into the breadboard, 78 ohm resistor or one that's close to that. It can be a little bit different, but don't make it too much larger or too much smaller. It just has to do with the height of the peak. So if you get too small, the peak's going to be very high. That peak output voltage will be very high. So we don't want to go too high for our oscilloscope. But yeah, that should be fine. Around there, you could go up to 100 or down to 50, probably be fine. A 100 nanofarad capacitor. The label on those, they're like, I'm not sure if it's labeled on the drawer. They're like the disc ones. Yeah, it says 104 on them. And a 10 millihenry inductor. Those are like black barrel inductors, and those are also found in the drawers. And then one BNC Y or T connector. I think that I put a Y connector at every station, so you should be fine. And one BNC cable just by itself. Two BNC cables that have the alligator adapters on the end. Some of them have them built into the cable. Others of them have a separate adapter on the end for alligator clips. And so have two of those. So then we build the circuit. Following steps describe how to build the RLC circuit. I'm not going to go into detail, but the main idea is that you want to measure your resistance and your capacitance using the multimeter. You can't measure the inductance using the multimeter. There are instruments that allow you to do that, but or we could make the measurements ourselves. But I'm going to punt on that one. I thought about having you guys do it, but I decided to let you guys just use the nominal value. Recognize that there's error involved in that, and you're probably going to be a major source of error because those inductor values are pretty nominal. They might be 10-20% off easily. So your theory and your experiment might not match perfectly, but it should be pretty good. Great. Build the passive portion of the circuit on the breadboard, so your RLC on the breadboard. Use the function generator as the voltage source. Its output resistance is 50 ohms. Use the TNC or the BNC T or Y connector to split the output. Split the output of the output. Just to split the output such that one cable connects directly to the oscilloscope's channel 1 and the other connects via alligator clips and jumpers across the circuit. So we've got our function generator, and it's got an output there. It's a BNC output. And we're going to put a Y or a T on there, so BNC Y or T. So I'm going to exaggerate what that looks like. That's a T1. So you're going to have a cable coming off here, and you're going to have a cable coming off here. One of them is going to go over to the oscilloscope. So the oscilloscope, I'm giving myself a little more room. The oscilloscope's going to have two inputs. One of those inputs, the channel 1, you're going to want to connect the function generator right up to the oscope, to channel 1. So you're going to we want to measure what the just lagged. Hopefully it's okay. We want to measure what the function generator is putting out in the oscilloscope. The other one's going to go to the circuit, so that's going to be some alligator clips and connect it up to our breadboard circuit as the supply, okay, as VS, with the source resistance as well as part of it. On the oscilloscope, and then we're also going to measure the voltage across the capacitor. So alligator clips cabled to the other channel of the oscilloscope. Okay. When it's set up properly, so we're going to measure then the steady state response at different frequencies. So it's a linear circuit. There's a sinusoidal input. And you're going to get a sinusoidal output. Remember, at the same frequency as the input. The only difference between the input and output is the amplitude and phase, right? We've gone through this whole discussion of that. If these two these two quantities that we will be measuring, specifically the amplitudes and the phases. So set the function generator to a sinusoidal output of 100 hertz. And it actually doesn't matter what the amplitude is, but I'm going to say a nominal, say like 5 volts peak to peak. It's a pretty good nominal value. It's sort of in the middle of the road. If you get too small, your accuracy is not that great for what the voltage is that it's putting out. And if you get too big, then you're going to saturate your oscilloscope. So don't want to do that. So take care that the output channel button above the connector is pressed to turn it on. So it's kind of weird on the newer function generators. You have your BNC connector that you're going to be connecting your cable to, and there's a little button right above it that you have to press to turn it on. So it's backlit, so you have to make sure that it's on, otherwise it doesn't come out. I've spent way too much time not knowing why I wasn't getting the signal I expected out of that thing, so it's good to keep in mind. Okay, so make sure that you can see the input and output sinusoid simultaneously on the oscilloscope. So we want to see, remember, we've got the input to the circuit on channel 1, the output from the circuit on channel 2 of the oscilloscope. We want to see them both on there. You might need to adjust the oscilloscope settings. Probably can just use AC coupling on both channels. Make sure you don't have any. One of the oscilloscopes, I was in there the other day, or today actually, and well, I guess technically yesterday. Anyways, there was a 10x probe setting set on the two channels. I don't know why that was set. We're not using any amplification on the probe, so don't use that setting. Careful of that setting. You're gonna get 10 times off, 10x off for your measurements if you use it. Make sure that your triggering situation is set up, and we went through how to use these in the first lab, but make sure that your triggering is set up so that you're getting a nice stable waveform on the graph. I would just trigger off of channel 1, for instance. Make sure your trigger level is set so it's nice and stable. Yeah, so set your oscilloscope up, make sure you're getting a nice, when you set it to 100 hertz input, you should set your time base so that you can see a 100 hertz wave reasonably well on the oscilloscope. So adjust it and get it tuned in, get it dialed in, and then measure and record the peak-to-peak amplitudes of the input and the output. Also measure the also measure and record. It's getting late. The time lag between input and output. So that's 4 measurements total. So make sure you get the frequency, the peak-to-peak amplitude of the input, peak-to-peak amplitude of the output, and the time lag. So the time lag is a little bit. So you're gonna have two waves on your scope, right? And I'll show it at a different amplitude. It's not great, but we'll pretend. So one way to measure the time lag is to measure the amount of time between peaks here. and we can call that like delta. Okay, so that's one of the measurements we're going to make. The frequency. So for those of you who are using the newer function generators, you can trust the frequency. You're not going to get a better measurement than that. If you're using the BK function generator, you're going to have to measure it. It doesn't give you, it's not a calibrated frequency. So you're going to have to measure it. You do that by measuring the peak to peak of the same waveform. So from one peak to the next peak, close to the peak. And then you just take the inverse of that, and you get the reciprocal, and you get the frequency. And then they should have the same frequency, so you don't have to do that for one of them. And then you want to measure the peak to peak voltage. Remember, peak to peak is from, here we go, peak down to peak. That's peak voltage of the input signal and of the output signal. So that's 4 measurements, and then record it. So repeat it and fill up this table. So down here is this table. Let's fill it up. So frequency measurement, get close to 100 hertz. So I give you all these different frequencies. What I did was I said from 100 hertz to 10,000 hertz, I want you to make these measurements on a logarithmic scale. And the reason for that is that you're going to get a higher density of points when you're in the lower. So when you go to these, when you're in these lower frequencies, you have a higher density of points. You use a logarithmic scale, and then you go to the higher frequencies, they trail off a bit, and that's because we're more interested in the lower frequencies. So we're gonna do that. I just generated them for you. I didn't make you guys come up with the frequencies. So if you're close, cool. You don't have to be right on the money. Just make sure that you write down what it is. So if it was actually 101 hertz, then write that down. Measure your channel 1 of your oscilloscope peak to peak voltage, the input. So when you're at low frequencies, you're probably going to be around 5 volts on the well, I'm going to let you guys find out. But and then the output, say 5 volts, and then your delay is however many milliseconds. Just go along here, fill this all in, and you're going to enter that data into MATLAB in your report to generate the graphs for your report. Then finally, so once you fill up that table, the last row in the table says peak for the frequency. So once you've done all those frequencies, you're just going to fiddle with the frequency and find the frequency that yields the highest output amplitude, and make a final set of measurements at that frequency. Don't forget to include this in your data. It will be obvious in your report plots if you don't include it. So the idea is that there's going to be a specific frequency that is going to be sort of a key frequency. It's going to be actually around here. And you're going to want to take a measurement right at that peak. It's going to make your graph look a lot nicer if you've got that. So do that. Okay, that's all for that. And then tips. So these are just tips for the BK, for the older oscilloscope. Don't use the fine tuning knobs on the vertical scale. So turn them all the way clockwise until they click for calibrated voltage operation. And similarly with the function generator, make sure that your frequency control isn't, well, that's not very precise, so make sure that you're actually measuring it So you're gonna dial it in on a like manual dial. So don't try to estimate what the frequency is from the dial. You actually have to measure it. So, okay. Report requirements, the usual stuff. What you're gonna do is you're gonna divide the output amplitude that you measured by the input amplitudes that you measured, and you're gonna get this R, okay, a function of omega. And when you do the circuit analysis, you can come up with a theoretical prediction of it, and then also the theoretical phase shift. So this is really similar to a lot of the homework problems that you did. You actually did one that's essentially exactly like this for an RLC circuit. You're going to do that, and then you're going to plot that, and then you're going to overlay the measured amplitude ratio data on that. Hopefully they match. They might be a little off, but they should be in the ballpark. Okay, so if it's way off, then something's going on. A figure with a phase shift. So you should have one with the amplitude ratios, and so the one with the amplitude ratios might look like this. It should start off somewhere around 1 at low frequencies. You're not going to go to 0, so it's down here. And then it's going to have a peak. So, and then it's going to drop down. It'll look something like that. And then your phase, so I'm just going to draw it right below. Your phase shift is going to be, it's going to start off at 0. It's going to go through a transition and go to about negative 180 degrees, negative pi. So that's the, those are approximately what you see. So you see the theory curves, and then you're going to see some data points. Maybe you're a little off, but they're look like that, and then you should be right on the peak with that extra point. That type of data that you're going to see. It is going to be bunched a little bit weird, and part of me is thinking that linear would have been just fine with this, but they're going to get a little sparse out here, points, but it should be okay. Alright, so that's it. This lab, I mean, I would say be very careful as you're taking your data, because it kind of takes a while to get the data. But the setup isn't too bad. The theory is going to take a little bit of work. Use impedance methods, though. Don't use. I mean, you saw it in your homework. If you do this problem with the chapter 2 methods, time-based methods, it's going to take a lot more work to find a steady state solution. So what you really want to do is use impedance methods for your analysis. Take your time, be methodical. It's really not that much to measure in this lab. You don't have to write any lab view codes, so yeah. That's all I've got for this week. So have a good time. Tip your TAs. All right.